Okay guys, hi, my name is Valeria. Today I'm going to be teaching you how to program autonomous for VEX Code V5. I guess this also applies to VEX Code Pro V5. It's basically the same. Um, this is going to be a time-based autonomous. So basically you're going to kind of adjust the times based on, it's not necessarily times, it's distances, but it's variable across robots. So that's how this video is going to work. First, I want to talk a little bit about the goal of your autonomous. So it's very important to have a plan before you begin. You want to communicate clearly with your team, have an idea of what you want to do. So first, I'm just going to pull up my screen. Here I have a little diagram of kind of the field for VEX. Now, something that you want to take heavily into consideration is autonomous wound point potentially if this is your program for pre-match autonomous. If it's skills, I mean, win point doesn't really matter. But if it's pre-match, you definitely want to think about it. So for this video, I'm just gonna program a pre-match autonomous. So let's say I'm a red robot and I'm starting. You can't start there. Starting like here or whatever. Can't start there either. So let's say I want to start like that. I'm gonna start at an angle, right? Let's say the first thing I want to do is pull, put down like a wing I have. So this would be step one. Then I want to move forward. That would be step two. Then I want to rotate. 3. Then I want to move forwards all the way down here. That's 4. Rotate here. It's 5. Actually, we're going to have this be 6, and then 5 is put wing down. So basically I'll put my wing down and then I'll rotate so then it'll touch there. So now that I have this plan out, I'm gonna open up a new Google Doc. So Docs and new opens one up. And I'm just gonna type this out. So so 1 would be wing down, 2 would be move 4, my formatting is bad. So move forwards to wall, and then 3 would be rotate like 115, no, 135 degrees. I'm just like estimating because I want to turn all the way over here, so that would be 135 degrees. Then move forward to middle barrier, and 5 would be rotate 90 degrees, to the right. And then 6 should be, that's 6. 5 would be put wing down. I actually forgot to note when to put the wing back up. So we're gonna put the wing up. We're not gonna put the wing back up at the end because that doesn't make sense to do so, because we want it to end with the wing down. Then what? I think that's it. Now I'm just gonna put in the speeds based on how fast I want to move. I want to move here at a kind of mildly slower speed. So we're gonna say, let's say 65% speed. We want to rotate at different speeds. There we go. Those are the spots we need speeds. Rotate 90 degrees, we're gonna say 70%. You're gonna give this a 90% speed because we want it to move faster when it's further away. It's a pretty long distance to move. And then rotate 135 degrees. We're gonna say 75% speed. These are kind of not relevant numbers. You can do it as you need. I'm just giving it different values that demonstrate how you could program it to change the speed. Because that's something you're definitely going to want to consider. You don't want to be running your robot at 100% speed at all times because you might be doing more detailed tasks in some part of your autonomous, and then other times you want to move faster because you're farther away. So let's define what kinds of functions we need to do to create, or whatever. So basically, for those of you that don't know what functions means, functions are basically a set of predefined instructions where you can change like the values. So let's say one of my functions is to drive laterally, right? We can input how much we want to move. So let's say we want to move 300, like 400 degrees forward. Then the wheels would all move 400 degrees forwards. If I give it a smaller number, it'll still move. It'll move the smaller number, but it'll perform the same actions, but with different kind of adjustments. So, like another example that I've given in the past is, let's say I have a cupcake recipe. The cupcake recipe is, I basically input the value of how many cupcakes I want to come out, and then it'll basically have the recipe for that set amount of cupcakes, and then the amount of cupcakes that I put in will come out, right? So let's say I have one cupcake I want to put in, then the recipe will basically do all of the work for one cup, have all of the ingredients for, do the math for all of the ingredients for one cupcake, and it'll output one cupcake, right? If I have 25 cupcakes, then it'll do the math for 25 cupcakes inside, make those cupcakes, and then it'll output 25 cupcakes. The same thing applies for coding. So let's say I want to drive 400 degrees, it'll do all of the movements that it needs to do to move 400 degrees, and then the output is a drive that will have moved 400 degrees forward. That's essentially how functions work. I'll explain it more as I program it because it's kind of weird to think about, but it works. Essentially, that's how it works. So we're not going to put in any specific amount of degrees because that's not the point. We want to make a function that, as long as we put a number in, it'll move that number of degrees, essentially. And then we also need a turning drive, right? Because we have moving laterally, so move forwards. This function would apply for forwards and backwards, and I'll explain later why that works. Turning drive. This would also work for left and right turning. I'll explain more of that later. And then we also need something for moving wings, or moving our wing, or like our wind point wing, up and down. Up and down. We also want a function to set our speeds, right? Because it's going to be tedious to reset the speed for every single one of our motors every single time we want to change it, because if you notice in my plan, I have that I want different speeds for every time our drivetrain moves. So we want a function that can help us with that as well. So now I'm just going to open up VEX Code V5. We're going to open it up. And this is why it's so important to remember where you stored your stuff, because you don't want to not know where it is, because you're going to use the same file project for your autonomous. Well, correction, you're going to use the same file for your pre-match autonomous. If you're making your scaled autonomous, you probably want to consider opening up a new file if it's vastly different. Okay. So this is what our code looks like so far. We worked on this last time. We're not going to be using our lift example this time. This could also be replaced for like a wing, but I'm just going to go along with the plan that I've already made. So this is our autonomous function. This is where we're gonna call all of these in order to implement this, right? I'm actually gonna change these to numbers because we can actually write down which function we would use. This should be function 3. I'm just gonna do this. Move towards wall is 1. This is 4. This is 3. 2. This is 4. That is 1, 4, 3, 2, 4. And I just want to do a quick note that these we're going to set, this is going to be like 80% speed. It's going to be 70% speed. And then this is going to be 80% speed. Now I'm not writing a function for this one because this is only one motor, so it doesn't make sense to create a function to run one line of code, and you'll see what I mean in a second once I start programming these. So this is our pre-match plan. If you want, you can do split screen, but I'm just going to be moving back and forth for now, only because it doesn't make sense for a plan like because I only have 4 functions and I already remember them all. So the first thing we have to do is initialize our new device. So I haven't initialized my wing yet. If you have done it, then you don't need to do it. That's the wrong thing. We're just going to call this wing. So that did that, and now we can start programming our autonomous functions. So the first thing we want to do is define all the tasks that we need to do, and then we'll start actually implementing those tasks in there. One last quick note before I start programming. Setting the speed is something you run before running this function. So anything that's within A is like preliminary to whatever is the actual number, which I'll understand more later when I actually start programming it. So first we want to define our drive lateral function. So this is just moving all of our like drives forward. So the way that you define this is void drive, let's say lat, because if you see, drive is already a predefined kind of thing that goes on in VEX, and we don't want to take that opportunity away from us if we ever need to use that function that VEX already has. The next thing that we're going to do is say double degrees. We're not going to use degrees because it turns orange, meaning VEX already uses it. So we're just going to use degree. I know it doesn't make sense grammatically, but we're just going to go along with it. So the next thing you want to do is remember all of the motors that we have for our drivetrain. So we have 4, which means we have to do the same thing for 4 different things. So we're going to do left front dot. This is when this little tab thing comes in handy. Spin for forward 90 degrees. So we can use that function because that one spins for a predefined amount of things. But instead of using 90, we're going to use our little variable name degree because that's what we're inputting every time we run the function. So basically this allows the variable to be replaced with whatever we put in our function when we call it. So spin for forwards degrees. This is why it's important that we didn't use degrees as our name here because we're using degrees here. Now we're just going to use the same line of code for the rest of ours. But we're going to replace these with different variables. Or there are different motors, is what I meant to say. So now the only thing you'll notice is that basically what will happen in this situation is that we have spin for blank degrees. It'll run this entire code, wait for this line of code to finish, and then it'll go to this line. So what we want to do is that we want to add a false just to kind of allow us to tell it to not wait for the next part. And we'll do these to all of our lines of code except the last one because we do want to wait for the last line of code to finish before we will move on. The next function that we want to do is turning our drive. So we're going to call another function. Void is just what it returns. So in this instance, we're not returning any value. We're just waiting for the actions to occur within that. Turn drive is what I'm going to call the next one, just because it makes sense and it's not any variable that VEX already uses. Once again, double degree. And we don't have to worry about this value being interfering with this value. Why? Because these variables only exist within these brackets. After that, they kind of disappear and they only reappear once you recall the function. So we're going to use the same thing, but the way that we turn is we reverse some values. So we're going to reverse our left values and essentially what that will do is that when we add a positive value here, this will move backwards and these will move forwards. Now where that is going to make us turn, we're just going to add a little quick note. So if positive, if our value is positive, then we're going to move to the left. If our value is negative, then we're going to move to the right. Because if you remember, if I just do a little diagram, if this is our drivetrain, that was a really bad box. That's our drivetrain, and our left moves to the back, and our right moves to the front. Basically, this one will move forwards, and this one will move backwards, making us turn to the left. Therefore, if we give it opposite values, then it'll move in the opposite direction because VEX is really nice. And if you give it a negative value within degrees, it'll move basically in the opposite direction that you intended it to. So if you give this a negative value, let's say you put in a negative value for degrees, it'll move right reverse and left forward, making it turn right instead. I'm just going to do a quick note for this one as well. positive equals forwards here because if we put in positive values, all of the motors move forward. If we put in a negative value, then it'll move backwards for connecting type. That's why I was saying that these functions apply for both sides. It doesn't really matter. Now we're going to write our wing function. So void move wing double degree. I'm just using the same one. And then we're going to say wing dot spin for forward degrees. Now there is no false on this one because this is the last line of code within the function, so we definitely want to wait for that to finish before we start doing anything. Now let's say wing forward. I actually don't know in this instance which way the wing would move, but in a theoretical world, let's say positive equals down, and then negative equals up. All of these values truly depend on if you have your motor set to reversed or not, because typically either the left side or the right side, or depending how you put the orientation of your motors, certain motors will be reversed. So you have to make sure you check first that all of your motors move forward when you say forward. If not, you need to go within your initialization tab and kind of put the reverse thingy on each of the motors that are going backwards. So keep that in mind. And then the last function we want to write is set speed. Okay, so void drive speed is what I'm going to call it, double speed. The reason I'm not calling it degrees is because we're not giving it anything that's degrees. So for this, we're just going to go in here and look for which one. So we're going to set the velocity. That's what VEX calls it, speed velocity. Technically it's velocity, but I'm not going to get into that. We're just going to use a different name just to make it less confusing. So left front dot set velocity. We're going to say speed and percent. Because once again, we're replacing the value with whatever value we want to get replaced there. So we're just going to copy this and replace it for all of our motors. So left back, right front, right back, and that's it. That's basically all of the functions we need to create for this situation. Make sure this is between 0 and 100. You don't want to burn out your motors. That would be very bad if you try to set it over 100. These are all of the functions you need. Basically now we're just going to implement them based on our steps. So for this, I am going to go into this kind of side-to-side mode, only because our tab is kind of big enough for us to do it if we put all of our other things away. So essentially, we're going to go down to our autonomous, and this is where we're going to implement it. So what I like to do is write out kind of the steps that we have. So this is step 1, leave a little space, step 2, step 3, step 4, 5, 6, step 7. So that leaves it nicely spaced out. So essentially now we can just call in our functions as needed. So first we want to put our wing down, and if we go to our function, we said positive values are down. So we're just going to do move wing, let's say 90. But first we have to set the speed. So the reason I didn't create a function for setting the speed of this is because it's only one line of code, so we can just say wing dot set velocity to 80%. Now you might be asking, oh, why'd you write a function for this if it's only one line of code? That's mainly because it's easier to just keep track of if all of your functions are the same. Also, you're writing out a lot more per each. You have to write forward, degree, degrees. This one's pretty self-explanatory as to how it works. You can 100% write a function for this. I think it's just not necessary, and it's just easier to see move wing here. So I'm just gonna do that. So then step 2, move forward to wall. So drive lat, that's what I named mine because we're driving laterally. If you don't know what laterally is, just moving in like a straight line, right? You're not turning or anything. So that one, we're not moving that much. So let's just say it's 300, right? 300 degrees. But we have to remember to set our velocity. So drive speed is 65. Now, something that I want to mention is that the degrees are the degrees of your motor moving. So when I get to the turning part, turning 135 degrees, your robot is not going to be 135 degrees. So when I get there, I'll explain that in a second. So then the next part is wing up. So we're going to set our velocity first. Wing dot set velocity. It is 70%. I can spell it right. And then we want to move wing. And we're basically going to do the opposite of whatever we did here to get it to the original position. Because if you remember, negative value is moving it up. Step 4 is rotating 135 degrees. Now, rotating 135 degrees is not you put in 135 and it'll move 135. Maybe it does, maybe you just got lucky, but essentially it's rotating your motor 135 degrees. So your motor is relatively small. Your motor is like this. This is where your axle is. It'll basically move from here to here. Like it'll rotate that. That's 135 degrees, right? Which is only moving your wheel like a tiny bit, right? So you want to take that into consideration. You're definitely going to have to do a lot of trial and error to figure out how much is 135 degrees. But I'll explain how to do that once I'm done setting up the rest of it. So we're going to set the drive speed to 75. Then it's going to be turn drive, I believe is the name of our function. Yeah. We're just going to say it's 600. And that is going to be negative because we're turning right. I forgot to write that in here. I wrote it down here, I just didn't write it up there. So that means we have to set it to negative. Step 5. Drive speed is 90. And then drive lat. This one's pretty far, so we're going to say 800 degrees. Then we're going to put our wing down. So we're just going to set wing set velocity 80%. And then move wing, we're going to say 90, and it's positive because it's moving down. And then the last part is drive speed 70, turn drive 90 degrees. So 90 degrees, let's just say, if we turn it 60 for 135, then it's 400. And that's right, so it's a negative value. Now, if your robot is ever not moving in the right direction, it might be that you miss a negative. So just go back and like delete or add a negative based on that. So this is technically all of the code to write this. For a design notebook, I would highly suggest maybe adding a picture of your plan, like what I had drawn out here, and then print this out based on your plan and then whatever functions you identified. And then when you print out your code, you can print out your functions and then add this, like this part of your code, and then basically be like, oh, these steps line up to our pre-match plan. So go there on page whatever to figure out like what each step is like supposed to do, or ideally you would have them right next to each other to demonstrate how it would work. Like have your pre-match plan next to your code in your autonomous void here, have it next to this, and then your functions basically next to this block that you have here. Now for testing, do not test more than one step at a time. And why I'm saying this is because if you try to test more than one thing at a time, you'll probably have a big goof somewhere, or you'll like try to do too many things at once and you'll miss a variable. It'll take so much more time if you try to do it out more than at once. So basically, the way that I would do it is if you do this little line of code and then at the end you add that line of code to determine that this is the end, it'll comment whatever is in between that. So by doing this, you can comment out a lot of code at a time. So what I would suggest is you test this. Does it move your wing as far down as you want to go? Then you, if it does, or if you need to add more like time or less time, then you'll adjust it accordingly. Then you move this little thingy down. You test the next part. Does it move correctly? Do I need to add more speed? Do I need to change the this value? Is it too short? Is it too far? Change it, test it. Basically, if it's moving too short, estimate like, oh, it's moving half of what I want it to move. So it'll be 600, or it's moving 2/3 of the way of what I want it to go. So it'll be like 450 or whatever. You can do the math, you can test it out. If you don't want to do math, then just keep adding values until it's actually there. My suggestion would be to just estimate as much as you can in order for it to make it more efficient. If you do one step at a time, trust me, you'll get through it so much faster than if you try to do the entire everything at the same time. So then you do it. But if you know that, like, now let's say step 3, you're changing the wings. If this value was originally wrong, maybe then you have to reconsider this value. Like, let's say this is actually 120, so maybe this has to be negative 120 to go back to its original position. Basically, you'll go down each step until you're done, and once you get all of your code finely tuned, you can remove that last part. If you want to see me do this with an actual robot, you can check out my VEX IQ autonomous video. Even though it's block code, it's the same principles of, oh, this is this far, so I probably have to go this much farther. I do it in like 10 minutes, a pretty simple code. And I have like a VEX IQ robot actually demonstrating it. So if you want to watch that, you can watch that. If you think you can do it on your own, go for it. But yeah, that's the end of this video. I hope this was beneficial for you guys on how to program autonomous. Once again, feel free to reach out if you have any questions on programming. But yeah, that's all.